Have you ever had an issue with a vehicle where you needed to analyse the engine data, only to realise that the information you see is much more complicated than expected? Sounds familiar? This is a first in a series of training modules on how to interpret scan tool data. In this video, we'll be covering gasoline engine sensors. One of the most important things to remember when diagnosing any fault is to slow down, be patient, fully read the description for the data, and document all your findings. One of the more basic sensors in the automotive vehicle is the coolant temperature sensor. On a correctly operating vehicle, the temperature sensor should operate between 0.2 to 4.8 volts and a temperature range from -40 to 140 degrees Celsius. This is what a correctly operating sensor should look like, from cold start to warm idle. Always check with the workshop manual for the correct operating temperatures. If you're not sure if the input data is correct, use a thermometer to confirm the sensor is reading the correct values. The NOx sensor provides vibrational information to the ECM for controlled ignition events. On a smaller capacity engine, the data would look like this: very minimal activity on a correctly functioning engine. Even when the RPM was increased, then snapped open, no real changes are seen. However, it might be necessary to road test the vehicle to replicate the engine's speed and load conditions. If there is a suspected fault in the NOx sensor, look at the data and check the spark advance and knock values side by side. There are three different ways the ECM may interpret accelerator pedal data: equal rising, rising falling, and split rising. So before any diagnosis is made, always refer to the workshop manual for the correct operating procedures for that vehicle. Looking at the engine data, we can see this system uses a split rising type. Both voltages increase as the pedal is moved. This is a correctly operating split rising APP circuit. So when reviewing data, look at the pedal percentage and compare it to APP 1 and 2 voltages. Look for any possible discrepancies. The throttle position sensor may also have three different ways of sending position data to the ECM. The data here is split rising. This is what a good value looks like. When reviewing TPS data, compare the throttle open percentage against signal position to verify the relationship between these values. The barometric pressure, or baro sensor, gives the ECM the exact ambient pressure values. A correctly functioning baro sensor value would be 103 kPa at sea level. Allowances will need to be made depending on your location. The MAP and baro sensors should read the same with the engine off and ignition on. The MAP sensor is an engine load device, measuring the absolute pressure within the manifold. Here is what a typical reading should look like on a smaller capacity engine from idle to around 3000 RPM whilst driving. If the pressure is low, so is the voltage. As the pressure increases, so too will the voltage. A quick integrity test for a MAP sensor is with the engine off and compare the sensor value to atmospheric pressure. They should be the same. So when checking the data, keep this in mind. At idle, the vacuum reading will be higher than what it would be at wide open throttle. It can be even higher again on deceleration. It might be necessary to get another tech to drive while you watch the data. The IAT sensor measures the air temperature as it enters the engine. This value will change depending on engine runtime and outside air temperature. On a warm engine and the ambient temperature around 20 degrees, this is what a good sensor should look like. On a correctly operating vehicle, the temperature sensor should operate from between 0.2 to 4.8 volts. The two most common types of airflow meters in current use by OEMs are the hot film and hot wire. Both of these sensors are similar in operation, as they both use a heated element for airflow sensing. The hot wire sensor generates an analog signal based on airflow that varies between 0.2 to 4.8 volts, while the hot film generates a digital square wave variable frequency depending on airflow. Here is a typical mass airflow reading on a smaller capacity engine at around 3000 RPM whilst driving. At idle, the voltage is below 1 volt and around 2.4 grams a second. Under engine load, the voltage is around 2.4 volts and the airflow is about 47 grams a second. Like the MAP sensor, a low voltage or frequency will indicate a low volume of air, while a higher voltage or frequency will mean more air entering the engine. One test would be to tap the sensor while watching the data. If there is a noticeable change, there may be an internal fault with the MAP sensor. The fuel rail pressure sensor plays a large role in GDI vehicles. It sends the rail pressure values to the ECM. Here are some typical fuel pressure readings for a smaller capacity GDI engine. At idle, the actual pressure is around 3 megapascals in 1 volt, and under load at 3000 RPM, the rail pressure sits at 20 MPa with a voltage reading of 3.6 volts. When diagnosing a fuel-related fault, look at the desired and actual fuel pressures. These should be nearly identical. Narrowband oxygen sensors vary from single to 4-wire. Like the name suggests, they can only sample a narrow air-fuel ratio. The operating range is between 100 and 900 millivolts for a correctly operating zirconia sensor, and may display as a rich to lean cycle, while a titanium sensor can display voltages between 0.5 and 4.5 volts. At idle, the sensor may be slow to switch, while under load at 3000 RPM, you will see the voltage cycle quickly. Oxygen sensor data can be tricky to interpret, especially if you haven't had much experience with wideband air-fuel ratio sensors. The air-fuel ratio sensor supplies voltage and pump current data to the ECM. This is a correctly functioning wideband air-fuel ratio sensor operating at idle and under load. 0 milliamps indicates the air-fuel ratio is equal to lambda, while a negative reading indicates a rich mixture with a positive being lean. At idle, the reading will be 0 milliamps. Under acceleration, we should see the value produce a negative current flow, and on deceleration, we would have a positive current flow. Post-converter narrowband sensors are similar to upstream types. They're used for catalyst efficiency monitoring. This data value must be checked with the vehicle under load after a suitable catalyst warm-up time. The value will fluctuate between 600 to 800 millivolts when in closed loop with a correctly functioning CAT. If while driving under load the voltage cycle is the same as the upstream sensor, this will indicate a failed CAT. The crank angle sensor provides engine position and speed data to the ECM. The sensor may be an inductive or Hall type. At idle speed, this is what we should see. The crankshaft sensor displays engine RPM. A great test is to watch this value while the engine is being cranked over. If the value drops out intermittently or is not displayed, there may be a fault with the sensor. Like the crank sensor, the cam position sensor can be either Hall or inductive. The cam position sensor provides cylinder event information to the ECM. This is what a good cam position signal looks like at idle. It should reflect the desired camshaft angle. The best approach to data interpretation is to know what the value should be and recognise what constitutes an abnormal reading. Thanks for watching. Bye for now.